Good afternoon, this is Schweitzer, and I'm going to summarize the big idea 5 laws of thermodynamics, describe the essential role of energy, and explain and predict the direct changes in matter. This particular chapter's got was it 5 enduring understandings, which you can take a look at. Conservation of energy. Okay, so it says energy entering and leaving the system can be classified in two ways: heat and work. Usually thermal energy is the heat, and work is movement caused by expanding gases. So you should basically understand the idea that if you take your car and you put gas into this car, maybe you'll make it an SUV, and the energy of the gas particle, let's say we got ourselves a random chain of carbons, and you put this into your gas tank, then all this energy, combustion chemical, looks like we got about 5, 6, 7, 8, 6 C8H18 plus O2 yields carbon dioxide and water, and then you're going to get some amount of energy that's being given off. Now this energy is takes many forms. One is it's literally going to be radiating energy off of the radiator, all that heat energy, but also the car is moving, and it's moving due to which is kinetic energy, which is due to the piston, and taking the piston, shoving it down real tight, and then as the gases explode inside here, it shoves the piston up and lifts the piston, doing work, which essentially for chemistry isn't as huge of a focus as, let's say, in physics class, where it's a main character in that class. But in this case, keep in mind that energy, Q, heat, and work, W, are going to be conserved. So whatever an amount of work is done on a system, then work is done. The work inside and outside of a system is equal. So system outside the system, if we have a negative Q here, then a positive Q here, and if I have a that's energy. So if I have a positive work here, I have a negative work here. So where you normally just see these terms is conservation of all types of energy. Second law of thermodynamics basically says that for any spontaneous process, total entropy of the system and the surroundings is going to increase. So you could say the entropy of the system. So let's just say the entropy of the system, okay, plus the entropy of the, maybe somebody see it as the universe, is greater than 0 for any spontaneous process. Again, we don't really use that a ton in chemistry class. It's more just a thread that, I'm not saying it's not important, but it's more of a thread that just shows how energy flows from one item to another item, and the spontaneity of different chemical reactions. But as far as the AP exam is concerned, only thing they would do is have a specific question that would understand that for a given system, yes, you can increase the amount of, or shall I say, you could decrease the amount of entropy in this thing. And let's make it an S, because that's what they use in everywhere else. If I decrease the entropy of this guy, then the exterior on the outside must have an increase of entropy. And if you add those two entropies together, it will be greater than 0. How much energy does a reaction give off? So again, there's many ways you can do this, but one way is to physically calculate the energy using a lab technique called calorimetry. This is a crude example right here, but it serves everything we need to know. We usually use specific heat for this: the mass of the energy of the collector, the temperature change of the collector, the heat of the collector. I often use this table here, known versus unknown. In order to determine unknown, you must have a known to compare to. So the known is our collector, and we have mass change in temperature, specific heat, and Q. And of course, these are equal but opposite. All right. Again, that's something that you want to be aware of. One last thing I'll mention about this is there's the idea of specific heat, which is C equals the energy needed to raise 1 gram of something 1 degree Celsius. So that is energy in joules per gram degree Celsius. And there's another thing called heat capacity. And this is a substance where you might have a heat capacity for the calorimeter cup. This calorimeter cup might have a heat capacity. And that is just going to be joules per degree Celsius. And this is where the mass is constant. And when the mass is constant, the mass is never going to change. So they just basically substitute the mass in for right here, and they just relate the energy per 1 degree Celsius. And that says, okay, if the water gained, 10 degrees Celsius, and the cup itself also gained 10 degrees Celsius, and if you want to know the total energy that this particular food lost, you need to know the energy that the water gained plus the energy that the cup gained. I would use specific heat for the water, this formula right here, and then use a heat capacity for this guy, which basically say, okay, every degree Celsius that this cup changes equals X number of joules of energy. And I would just simply multiply the number of degrees Celsius times the heat capacity, and then that would give me my total amount of energy that the cup gained, and energy that the water gained gives me the total energy that this item lost. So this is a energy per degree Celsius, but when I multiply it times the degree Celsius, it just drops out the Celsius and gives me energy in joules. How much energy does a substance give off? Okay, so here's another scenario. Now again, I have two circles here, a system before and I have a system after, but in reality they're the same system. So this is a snapshot picture before, and this is a snapshot picture after. So if I could measure the system before for energy, measure the system after for energy, subtract those two items, then I would have the difference in energy between the two. And so what we do is we do all of these things, or that particular methodology. Take a system, take the total energy of it beforehand, or so they do the products minus the reactants, which that's just a mathematical formality. They're being consistent in all of them. Products minus reactants, products minus reactants. And then you can see the difference between the two. And that tells you whether energy is exiting the system or whether energy is entering the system. This is another good diagram right here, which is your heating curve. Again, this just shows a snapshot before, snapshot after, activation energy. This is the difference in delta H. Notice that the beginning and ends never change. It's just this would be controlled by a catalyst, but either way, pretty important here to know how to use these formulas to calculate the delta H, delta S, and delta G. How do I quantify the amount of energy given off? Okay, well, in this case, it depends. It depends what they want you to find. I mean, do they want me to tell me just a total amount of energy? Like, for example, in this example right here, they want to know how much energy this thing gave off. Well, then I can quantify it in just kilojoules. Do they want to know how much energy per gram of that food stuff? Well, that's another scenario. So it could be just plain kilojoules. It could be kilojoules per gram. Okay, well, what about if it's a chemical reaction? Well, then sometimes they do just kilojoules per reaction process. And they don't usually put this on here, although I see it getting more and more common that they will list this little guy on the end. So what they do is they basically take a balanced chemical process and they say, okay, well, this is the amount of energy it gives off when one loop of this reaction. So 1 mole of this, 5 moles of this, 3 moles of this, 4 moles of this are involved. These are consumed, these are produced. and then this is the amount of energy involved, and at that point it's just a proportional problem. So this is a pretty important concept. 50 grams of propane is burned. How much energy is given off? So in some sense, it's just a proportion. So it's 50 grams. Get rid of grams and go to moles, and then get rid of moles and go to okay, so this would be the molar mass right here. So you can add the molar mass of this guy and plug it in here. And then for get rid of moles and go to kilojoules of energy. Now that means that for every 1 mole of propane, I get out, in this case, X kilojoules of energy. And if it's negative, which a combustion reaction would be, then that's just it's being released. So be careful if they ask you how much energy is being released. You could just put down the kilojoules. But the negative is just telling us that it's being released. So they ask for delta H. Delta H is always kilojoules per mole. So, but per mole means per reaction. So, in this case, this would give me the actual kilojoules when 50 grams went through the process. The delta H is this guy right here, which is the kilojoules per mole of the process. Per 1 mole of this guy, per 5 moles of this, per 3 moles of this, and per 4 moles of this. So if they ever want me to calculate delta H, I'm always going to go kilojoules per mole. And you would use possibly this equation here to get the kilojoules. So maybe you have a collector that's collecting energy, and then you want to divide it by the moles. Now, you'd always want to use, well, I mean, you use whatever they give you, but if they give you 2 reactants, you'd want to use the limiting reactant mole. All right, a heating curve, pretty common. We'll see these around quite often. What do you want to know about these things? Well, okay, first things first. As we increase and as we add energy to this thing he absorbed, we warm. Now, anytime we warm something, we're going to use Q equals the mass change in temperature times specific heat. Okay, so they'll give you a specific heat for, let's say, this item as a solid, which is fine. And you just plug in your values and solve for change in temperature or whatever they want. Very important to note that this is the same temperature as this right here. So we have 2 little spots here. They're the same temperature. In this case, you're saying it's 0, so it looks like this is mimicking water. So you can have solid ice at 0, and you can have liquid water at 0. All right, so any energy added during this process is just converting from phase, from solid to a liquid, no increase in temperature. So can you heat something and not have it warm? The answer is yes, during a phase change. So how much energy is given off here? Well, it's delta H of fusion is what they call this. Fusion is just this conversion here. And it's just going to be in a kilojoules per mole. So I want to know how much energy something gives off. And it's pretty common for them to give you, in the multiple choice, a pretty easy numerical value that you can do in your head or pencil it out to know how much energy things will change. Again, here it will be Q equals the mass times change in temperature times specific heat. And then here, to go from this area, notice how big this is. A lot of energy needed to go from a liquid to a gas. Lots of movement that needs to be established. And of course, this is delta H of vaporization. And this is given in kilojoules per mole. I also would point out to you, just so you know, that 4.18 joules equals 1 calorie. And by definition, 1 calorie is equal to the amount of energy needed to raise 1 gram of H2O 1 degrees Celsius. And that's how much a calorie is. So this, where would you see this? Well, if they wanted to make the math simpler on a problem like this, they could just put everything in calories, and they could make the mass 1 gram, and they could move around here a lot easier just using a calorie. Heat capacity versus specific heat. Looks like I got ahead of myself a little earlier. Of course, a specific heat is the amount of energy needed to raise 1 gram of a substance 1 degree Celsius. Okay, I just mentioned that right there. Heat capacity is the amount of energy it takes to raise 1 gram of substance 1 degree. Amount of energy it takes to raise 1 gram of substance 1 degree Celsius. The the mass of these situations is locked. So the heat capacity, I guess I should correct this, is not necessarily 1 gram. It's just whatever the mass of the item happens to be, that is what that particular item is. Like I said earlier, you have like a calorimeter cup. The cup isn't 1 gram, but it still has a heat capacity. So the mass is just locked, and you would have a specific heat capacity for a specific substance. And here's the calorimeter cup example. Even if you place a thermometer here and you're measuring the temperature, as the cup, as the water gains energy, as the cup gains energy, so does the thermometer absorbs some of that energy. And of course, we always kind of talk about this thing as well as, I guess a little side note here. Whenever we're doing this kind of work, if I were to take a block, this always throws kids off. I take a block and throw a hot block, let's say 100 degrees Celsius, drop it in here, and the block absorbs energy. I'm sorry, I should say this. The block releases energy to its surroundings. The water absorbs the energy. So in this case, this is an exothermic process because the block is exiting energy to its environment. The water just happens to be absorbing it. So this is very exothermic. And you'll notice that the water will get hotter. Alright, so then you take another cup, whatever, throw some water in it, and you throw some chemicals in it. Let's just say NaOH. Throw this in here, and the chemicals dissolve, and they dissolve here. And in the process of dissolving, they radiate energy to the surroundings. Now, the water is the collector in both of these situations. They're both going to follow Q equals mass times change in temperature times specific heat. And in this case, you'll notice that as the water gets hotter, okay, the chemical process of going from NaOH to Na plus plus OH negative, it's giving off energy, so its delta H will be negative. So this is also exothermic. Keep in mind, anytime your collector gets colder, it's endothermic. If your collector gets hotter, it's exothermic. The water is the collector in this case. It is releasing energy to its surroundings. If this substance, let's say sometimes they use like ammonium chloride is a common thing used in freeze packs. So you drop this into water, this chemical into water, ammonium chloride, and you drop it in, it dissolves, and it absorbs energy into its little particles. As it dissolves, it takes energy in from the surroundings, and therefore it gets colder. The water gets colder because it's losing energy to the chemical reaction, which then stores it as potential energy for later on. But either way, it's this process, the NH4Cl going to NH4 plus Cl minus, energy is entering the system from the surroundings for that process to run. Enthalpy. So enthalpy is kilojoules per mole, and this is of course delta H. I've talked about this quite a bit already. What is it and how do I calculate it? Again, I've talked this a bunch already. It's just as a reaction proceeds, it's the amount of energy needed for it to cycle through this process one time. Ways to calculate this thing, there's a bunch of them. Okay, so we have using our thermodynamic tables, very common. These are based off of our relative scale of formation from elements. Keep in mind, elements are 0 in this case. So this is one way which we calculate this, and I'm not going to go through a whole example of how to use the thermodynamic tables. You should be able to do that. Don't forget the elements are in fact 0 there. So either way, bond energies. Okay, so bonds broken minus bonds formed. This is now bonds break in the reactants. They form in the products. So this is one where we're doing the reactants bonding, subtracting from the products bonds, which is backwards from how we normally do it. Keep in mind that when you break a bond, and some people just, I don't know why this causes people problems, but let's say a hydrogen bond is a reactant. When I break this bond, I need to add energy. So breaking bonds, you might say, is endothermic. And because you're separating two different things. And when I form a bond, it is, let's say this HCl bond that's on this side. When I reform this, well, then energy is given off. So we're comparing about how much energy goes in during the reactants and how much is exited during the product forming phase. And again, I'm not going to go through an example of these. You should be able to draw all the structures out, add up all the bond energies for each of the ones that are being broken versus the ones that are formed, subtract them, and show all your work. Hess's law, again, is another important thing you should be able to utilize when you want to figure out how much delta H for an individual piece. You should be able to manipulate the equation. Remember, flipping a reaction flips the sign. Multiplying a coefficients multiplies the delta H, so then you add them up. Entropy, quantity of disorder. So again, we've talked a lot about entropy as well. We're kind of circling back. We talked about this a little bit right in the beginning as far as the second law of thermodynamics. But entropy essentially is the amount of movement or the amount of disorder. I often refer to this as movement. I'm not the only one, but it's something that way I kind of describe it. So you should be able to do a couple things here. One, you must be able, this is important. There was a problem in an exam we just had recently where you would need to be able to estimate the delta S sign. That's quite common. And we look at this and say, okay, well, as I go from reactants to products, am I gaining movement or am I losing movement? Am I gaining movement or am I losing movement? Not the most difficult thing in the world, but obviously as you go from gases down to solids, you're losing movement. As you go from solids back up to gases, you're gaining movement. Producing gases usually is an increase in entropy because you're increasing movement. All right. And you'll find as well, even on our heating curve, it looks like this. We just saw this not too long ago. As you go from a solid to a liquid to a gas, you are going to be adding energy to this thing. So as you add energy, you're going up this thing. Add energy, you're going up. As you add energy, you're gaining more and more and more movement. As you come down from solid to liquid, you're very fast moving gas particles. As you come down, you're exiting energy and your particles are slowing down. Exiting energy and the particles slow down. Exiting energy and the particles slow down. Important to it doesn't seem like this is that important of a chart, but really there's a bunch of questions that come and go from it. Spontaneous or non-spontaneous? It's will a reaction proceed spontaneously or proceed towards the designated products to the right? So we have in this case for a reaction just to go from reactants to products. This is of critical importance. Will it happen all by itself, or do we need to invest energy to drive it that way? And it's no different than if we have say a rock, and I want to pick up the rock. I'll need to invest energy to pick up this rock, and then eventually, as I invested that energy, the rock will then, as I invested, can fall down on its own. So the question is this thing, or you might even say it's on a hill or whatever. You could roll the rock up a hill, and like so. Okay, the rock's down here. Roll it up the hill. And then in that case, the rock now has the ability to roll down the hill all on its own. Where is the rock? Is it on top of the hill or is it at the bottom of the hill? Does this reaction represent the rock up here, or does it represent the rock down here? If this chemical reaction represents the rock up at the top, then this thing's going to flow towards products all on its own without having to have me or anybody else invest any more energy. As opposed to if this chemical reaction represents the rock at the bottom of the hill, it's plain to see that rock's not going to go to the top unless we invest energy to get it up there. So ultimately, that is what we're trying to figure out. There are several factors that affect that, and I'm sure we'll discuss these right here, and we will. So exergonic is a term describing delta G only. And if it's negative, then this reaction is running It is currently running. That is all that is said about it. It is running. There's a net loss of energy and will be spontaneous. So the system is losing energy, has a net loss of energy. In this case, this involves delta H and it involves delta S. And temperature is a concerning factor as well. In fact, you could even say it's delta H, and the other factor is delta S times the temperature. So these are two factors that affect them. In fact, they are right here. So one could be these together add up. Oh, this is a negative sign on here, but they will combine additional wise. Whether it's negative or positive, they will combine, and that will add up. So if if delta H is causing it to be negative or delta S causing it to be positive, blah blah blah. Either way, together we get a net effect of delta G. Are we gaining energy, or are we losing energy? If we're losing energy, negative, then this thing will run just a matter of time. It's losing energy, and it's just a matter of time. Positive delta G, net gain of energy, will need to be fed energy to constantly keep it moving. So this is like something being at the bottom of the hill. Is it impossible for a ball to roll up a hill? No, as long as we are pushing it constantly. That's a positive delta G. Factors affecting this will be delta S, as I mentioned. If it's positive, then this is a spontaneous factor. Gaining movement is spontaneous. Things stopping and slowing down, that's harder to do. And it requires energy to stop something. Delta H is enthalpy, and a negative enthalpy also a spontaneous factor. Losing energy is spontaneous. Temperature affects entropy right here. Okay, using mathematical formulas, okay, to calculate delta G. So things you want to be able to do here. Calculate delta G here, calculate delta G at alternate temperatures. So we can take and sub in a new temperature and see where this, what delta G will be. Now keep in mind, if delta G is 0, that's just in the cusp of a negative delta G and a positive delta G. And this one here is non-spontaneous. This one is spontaneous. So at this cusp right here, the reaction is kind of between, will it run or won't it run? So whenever we want to know if a reaction is going to run spontaneously, I substitute 0 in for that guy, substitute this guy's delta H, this guy's delta S, and solve for this temperature. That's a pretty common thing. Note that these are calculated at STP. So changing the temperature, there is a certain amount of error involved. You should be able to, if given some of these pieces, you should be able to solve for delta H if given delta G and delta S temperature. Same thing for delta S. There's two ways to calculate delta S. One of them is if I give you delta G, delta H, and temperature, you solve for delta S as the missing variable. Or you can use your thermodynamic tables. Remember, like I said, the delta, what those little prime symbols here mean. STP, 25 degrees Celsius for that. Although all the other places around generally STP is 0 degrees Celsius. So for gases, STP stands for 0 degrees Celsius, but here it's 25. Just talked about this a second ago. Like I said, temperature reaction becomes spontaneous. As I mentioned, as your delta G is sort of teeter-tottering on 0, is whether a reaction is going to be, going or not going. So we solve 0 and solve for temperature. Delta G prime versus K versus electrical potential prime. It's important just to understand, I guess, memorize these signs and see what they mean. So if I have this particular drawing here, and I use this drawing a lot, and let's say this is the end point. The end point represents where we end, so I look at this as like a dial on a speedometer, and this represents the end pointer K. So K is equal to the ratio of concentration of products over concentration of reactants. And once we get to this balance of certain amount of product and certain amount of reactant, in this case, I guess I should say that I don't really use that a whole lot, but essentially the fact that I'm more to the right means I have more product than I do to the left. That's how I use this drawing. So this particular value here, the K on this guy, the K is greater than 1 because I have more product than I do reactant. Okay, so that's just this idea of how this little dial works. But in this case, if I'm right here, okay, I'm not at K, so my ratio of products versus reactants is not the same as it would be if it was right here. This ratio of concentration of products over concentration of reactants, we often refer to, we do all, it's referred to as Q. So eventually Q will adjust to become K. To do that, I would need to lose reactant and gain product. This is product favored. I would need to go this way or rotate this way. Okay, so whenever we look at a delta G, whether it's a prime or whether it's not a prime, it doesn't really matter. If it's negative, that means this reaction is going to proceed towards products in order to get to a situation where its K, its Q will equal its K value. Now, in my drawing, I often use this portion right here in the middle to equal my STP starting location, STP. And if your delta G prime is here, then you know that this is always the same starting location. Therefore, K is going to be this way, and if it's negative, and therefore, if your delta G prime is negative, then, okay, because you're starting from the same spot, your K has to be greater than 1, because if you're right in the middle, and at STP, all concentrations equal 1 molar. So no matter what we use for a chemical reaction, when you put 1 molar in for each one, then your Q or your K at that point would be equal to 1. So either way, if I start STP, my Q equals 1, because no matter what I do, squaring or not squaring, my Q will equal 1, and therefore I can move to get to my K. So a little bit more discussion there than I thought, but either way, and then you should note that, of course, if you have a negative delta G, that means you're going towards products. A positive electropotential means you're moving to the right, towards products. And then assuming that you are, that you're starting from STP, because if you're starting from way over here, then you could rotate this way to get to your K value. So just keep that in mind. But generally speaking, these guys are associated with a K that is greater than 1. And all of this is reversed for a endothermic reaction. Okay, more of the same stuff here. Kind of just talked about the last slide. STP, delta G prime, and E prime have calculated values that won't change. Okay, so that's important. Sometimes you see it. These guys are representing essentially where we are at the start. And so we have delta G prime. It's just like, it's like a sign. It's a street sign. It says, okay, by the way, K is, if it's negative, that far, it's going to the right. So it's an arrow pointing that far. And then the value of it tells you how far. Like how far, many kilojoules, how far that way is it. Technically, okay, the delta G prime is only valid at this location right here. Delta G prime is only good at this location. Once we start losing reactant gaining product, let's say we're right here, we don't call it delta G anymore because the concentration is no longer 1. We just call it delta G. And of course, when delta G reaches the endpoint, delta G equals 0. And that is critically important. The electropotential also equals 0. So we've basically come to our equilibrium or resting point. All right, so this is some thermodynamic equations, or I should say thermodynamic questions from a recent test. So this is talking about number of energy of gas particles or some particles as we change temperatures. Now, notice that when we say energy temperature, it's kinetic energy, which is the average kinetic energy, and this is equal to 1/2 mass velocity squared. And sometimes they'll say average velocity. Well, this is slightly different. It wants to know the speed of the particle, not just the energy. This is referring to this little value right there. Either way, you should note that for any size, any kind of a sample of particles, some particles are traveling fast and some particles are just sitting still. So at any temperature, we're always going to have some particles sitting still. So we always come off the 0 point. The area under the curve here represents the total number of particles. So in this case, the dashed line is the hotter one. So this is the original one. This is the answer here, I do believe. And you notice that area there looks like it approximates the same area as this guy right here. So the area under the curve has to be the same. So in this case, these two are not the same area, so they're not the same number of particles. These are the same area, they're not the same particles. And of course, we know that as we get hotter, here's the answer key. As we get hotter, we want to have the average to be larger. So that's why this is the answer, and not this one. This one might have the same area under the curve, but in this case, the average is farther out. So this thing, which the following shows speed distribution is the same amount at a lower temperature. Okay, so the average is obviously lower, it's more to the left. Particles are slowing down, whereas here they're moving farther out. So the average particle is moving faster. All right, next one, it says a 100-gram sample of metal is heated to 100 degrees Celsius, then quickly transferred to an insulated container holding 100 grams of water, blah, blah, blah. Okay, so it changes temperature. So we have this object of something, that hot block scenario we talked about earlier, drop it in, and it radiates energy from one thing to another thing. So it's important to understand that this thing will radiate energy from the block to the water until the temperatures are equal to each other. Not until the energy transfers. This isn't necessarily, well, whatever energy is lost by the block is gained by the water, but just because the, well, I shouldn't say till the temperatures are equal. Well, yeah, they'll transfer till the temperatures are the same. And then the thermal transfer of energy back and forth ceases. Okay, so before I get too much stepping on my own toes here, the metal of the temperature changed more than the water temperature did, but the metal lost the same amount of energy as the block gained. So again, that's very important to understand that, of course, the block in the water are going to, whatever energy is lost by the block has to be gained by the water. But as an item gains and loses energy, all right, as something gains and loses energy, the rate at which its temperature changes is basically specific heat. So Q equals mass times change in temperature times specific heat. That is what specific heat is. And since they have different specific heats, as they transfer energy back and forth, the temperatures change. And this transfer will occur until the temperatures are equal. All right, so here the average kinetic energy of gas molecules is, well, because they're all the same temperature, they all have the same energy. Be aware that they say average anytime you use the word velocity. Okay, well, that's a little different. In this case, we'd say, well, they usually for velocity, they say for a given energy, which of these guys has the highest velocity? Well, 1/2 mass velocity squared equals kinetic energy, and all these things have the same kinetic energy. So the more the least massive particle has the largest velocity. So this guy would have the highest velocity. This has the lowest velocity. All right. Here we have a picture. It's big enough that I couldn't fit it on one slide, but this is essentially an energy picture. This is a picture basically of a ball at the bottom of a hill, and I'm investing energy in to raise the ball to the top of the hill, and then it rolls back down. So energy in equals energy out as it rolls back down. So this thing is basically saying, okay, the dissolving of an polar solvent can be imagined as occurring in 3 steps as shown in the figure above. Now, to be honest, this is difficult just because how odd this question is. It looks really strange, and it's one of the first times I saw it. I'm like, this looks really strange. And you just kind of got to piece through it and think of it just as purely as energy. So anyways, result 3 steps as shown in the figure above. in this step, separation between ions and solute is greatly increased, just as it will occur when the solute dissolves in a polar solvent. In step 2, the polar solvent is expanded to make spaces for that the ions will occupy. And last, the ions are inserted into the spaces of the polar molecule, which are the following. Best describes the delta H for each step. Okay, so essentially we have 3 steps. This step is separating particles, so this is requires energy in. Step 2, of course, separates particles apart, so energy must go in. So the first 2 steps require energy to enter the system, or would be like endothermic. And then finally they come back together, and they retract back together, and therefore some energy is being released. So it's a matter of it's like lifting things. As you separate them, you must add energy. As they come back together and fall back down the hill, you get energy back. So the first 2 are endothermic, and the third one is the final one is exothermic. Kind of unusual problem. All right, in this case, it's how much energy heat is released or absorbed when 0.05 moles of chlorine is formed. All right, so they're saying here that, well, half a mole of chlorine will give me 437 kilojoules of energy released. So at this point, I can get rid of the absorbed altogether. So it says the elements, it says how much heat is released or absorbed when 0.05 moles of chlorine is formed from. So this is the first time I did this problem too, and I didn't read it fast enough because this thing is backwards from the reaction. So that'll probably catch a lot of people. So they want you to go the other way. They say how much energy is absorbed when 0.05 moles of chlorine is formed from KCl, going this way. So the released are out, and we got to go to this guy. And if we had 0.1 moles of this guy, it'd be 43.7. Well, I shouldn't say that. If we had half a mole, it would be 437 kilojoules of energy absorbed. And since I have 0.05, just proportionally, C is the answer. And there you go. There's your answer key if you want to pause and look at it. The next one is, okay, which the values for delta H for a process in the table are less than 0 indicate exothermic processes. This again is a more challenging question, but it just comes down to, do you have to add energy or don't you? So in this case, I want to look at this thing and say, well, okay, from a solid going to a gas, that is going to be this chart right here. And you should be aware that as you move up the chart, you got to add energy in. You're going from a solid to a liquid to a gas. This is going to be highly adding energy, which is endothermic. This guy is endo. Anytime you add energy, it's endothermic. All right, so now in this case, I have potassium gas, potassium going to a potassium plus, and a negative electron being removed. Anytime you have a positive nucleus and you have an electron here, to remove an electron, separate a negative from a positive, you must put energy into the process. It's like lifting a rock. Rocks don't lift themselves. Charged particles don't separate themselves on their own. This is endo. All right. In this case, going from chlorine molecule to just plain chlorine atoms. So I'm going from this guy to just simply chlorine and chlorine. Anytime you break a bond, energy must be invested. This is important, little small details. This is endo. All right. Conversely, anytime you have a positive and you want to bring an electron near it, the electromagnetic waves or Coulomb attractions will automatically bring that electron in closer. I don't have to invest work. It's like a ball rolling down a hill. I don't have to do anything. This is exothermic. And finally, to bring a positive cation and a negative anion closer together, that's the same thing as being two opposite charges. And again, I don't have to invest any energy. In fact, energy is released in this one and this one. Exothermic means energy is released. So Y and Z are the only ones that are exothermic. This is an important concept to think about and make sure it makes sense. And there's the answer sort of dialed in. You can take a look at it. All right. It is observed that the reaction produces KCl from elements, goes essentially to completion. Which the following is a true statement about the thermodynamic variability of the reaction? Okay. It says, so the reaction is favorable and driven by enthalpy change only. So as we look at this thing, we would look at this formula and say, okay, what about this formula makes this negative? All right, so look at the pieces. Say, well, it's negative, so the delta H is negative. So this is negative, which helps this be negative. And if this is, hypothetically, if this was positive, which it's not, then a positive times a negative is negative, it would also help that thing. But that's not what's happening. So it turns out that looks to me like this delta S is a negative. And negative times a negative is a positive, and that's fighting against this thing. So in this case, the only thing that's helping this thing become negative is the delta H, and it's being hindered by this guy. So that's why the answer is A. And how do I know this is negative? It has to do with movement changing in the reaction. Losing movement. I'm losing movement, so I'm losing disorder, and therefore it's a negative delta S. All right. This reaction, this problem I think would be one of the tougher ones on the fly, a little more tough. So elements of potassium and chlorine react directly to a compound. Okay, blah blah. So I have this thing forming, and which of the following expressions gives me this guy? It's kind of a electrochemistry Hess's law. So all I do is I take this thing, I start sketching it out, and again, this takes time, it takes patience. I want to know this guy. Of course, to get this guy to equal the overall, in this case, I took this reaction, which is it's only dealing with X and Y, these two guys right here. That's important. Don't worry about all the other guys. And of course, I need two half reactions to get an overall reaction, which is going to be X. That's X. So I know I can't manipulate really Y and X to get, well, together. So these two go together, two halves, and they're both reductions. So I'm going to flip this one so that I get this ending result. As I flip this one, I get a negative. So in this case, as I solve for my question mark, adding these two things together, of course, this thing gets multiplied times 2 in order to match these up. So flip and multiply times 2. Of course, we're dealing with delta H's here. I don't know why I mentioned electrochemistry earlier. This is just straight, well, I guess because we got some half reactions here. Either way, it's still just a thermodynamic Hess's law problem. So I need to flip this guy and multiply times 2. And I'm going to get question mark minus, only because it's negative, 2y equals x. And then, of course, y equals x plus 2y is just solving this for the question mark, and that is my answer. Question C. It's right here. Let's see. A little tougher on the fly. And that is all the questions. Thank you very much.